At this point, we've seen quite a few buffer overflow vulnerability types. So we had array overflows, we had off by one overflows, we had unterminated strings, and of course just regular contiguous buffer overflows. Now what they have in common is that they all have a very easy path to overwriting the return address, which is simply on the stack right after the buffer. So if we're going to consider other cases, then we need to consider other variants of the exploit. So let us give this some thought. One case is where we can overflow a global variable. Global variables are stored in the data and BSS segments. So these segments are in the L file and they're loaded when your program is loaded. The data section contains initialized data, so this is actually stored in the binary, whereas the BSS contains uninitialized data, which will be initialized to 0 by the operating system. Now, these sections are in a completely different location in memory than the stack is. This means if we have a contiguous buffer overflow, we're not going to be able to reach the return address. Can we still exploit these cases? Well, it turns out we need to learn some new techniques to do this. So there are alternatives to hijack control that we could use. So instead of overwriting the return address, we can overwrite something else that allows us to take over control. One example would be overwriting a function pointer. So function pointers are occasionally used where you want to specify that some other function can call different functions depending on how you call it. So a typical case would be callbacks. You tell a function to do something for you and to call one of your other functions based on the result. So this is a typical case where you use function pointers. Now if you overwrite a function pointer, the impact is very similar to overwriting the return address. Instead of having overwritten the code pointer in memory that is used on the return instruction, now this pointer is used in an indirect call instruction, which fetches the target of the call from memory. This target is now corrupted, so it's going to call whatever function the attacker wanted to call instead. Another option, if we want to hijack control, is overwriting a frame pointer. So if for whatever reason we cannot overwrite the return address, but we can still get somehow to the stack, we could overwrite the frame pointer. Well, if we change the frame pointer, it means we're pointing it to a different stack, in effect. What can we do? Well, we can basically set up a fake stack somewhere, for example in the data and BSS segment, point the frame pointer to it, and then later use this stack to return from. This is also an option. In some cases it might require more vulnerabilities, but it allows us to use vulnerabilities that do not allow us to reach the return address itself. Another option in C++ is to overwrite an object pointer. So C++ objects allow you to make virtual functions. So deep down, virtual functions are implemented by putting a pointer to a table of virtual functions at the start of the object. We will go into more detail later. For this case, however, it suffices to explain that simply this pointer points to a table of virtual functions. And if we replace the object, we can point it instead to some other location. Now, if this other location contains code pointers, then the first time a virtual call will be made, it uses these code pointers to perform the call. So this is another case where we can hijack control. It's similar to function pointers, but of course virtual functions are very commonly used in C++ code. So this is a common effective attack vector. Now, we don't even need to hijack control in all cases. In many cases, even just overwriting a variable breaks security, even if the attacker does not gain control of the program. A typical example would be overwriting strings to bypass authorization. So let's say that we have a string pointing to a temporary file, and we overwrite the string to point to /etc/shadow. Now we might suddenly be able to do all sorts of scary things with the shadow file, instead of with the intended and harmless temporary file. Other cases include changing integers. So, for example, index and size variables will often allow further overflows if you get to them. So if you have an integer in the BSS segment or the data segment, that is used as an index somewhere, or that is used as a size for a bounce check, if we overwrite this, it means that we can perform an array overflow somewhere else. Well, this could be very useful for the attacker again. Other options include UID variables. So if they are passed to set UID, then this influences the amount of privilege that we have, which can be an important step in an exploit trying to escalate privilege. So of course this depends a bit on the context, what we want to achieve, but there are many ways in which integers and strings can be useful. And then of course we could change pointers. Whenever we change a pointer, it essentially achieves the same thing as when we override the thing that it points to. So if we have a pointer pointing to a string, we can just point it to another string that we construct in the data or BSS segment and use the string instead of the original, again achieving, for example, authorization failures. Now this can also be used as part of creating an arbitrary write. So if we can change a pointer and somewhere else one attacker controlled variable is written to the pointer, it means that we control both the location where the write occurs and the value that is written. Now if we control this, we have what is called an arbitrary write, and it basically always allows further escalation. So for example, if we know where the return address is, we can use the arbitrary write to overwrite the return address. And this also goes, of course, for all the other options for control flow hijacking. I have mentioned a couple of times how buffer overflows are super common in real software. However, you don't necessarily keep all your buffers on the stack. So, in fact, heap overflows are probably much more important, because the heap is a very logical location to put large buffers, which of course often have a potential for overflowing them. So the heap is used by functions like malloc, new, and other explicit allocation functions. So these functions give you memory that survives the return of the function. So if we have a local buffer on the stack, it will be deallocated whenever we return. If we allocate memory on the heap using malloc, new, and friends, then we must explicitly deallocate the memory. If we do not do this, we leak memory. And this is also an issue, because eventually the program might run out of memory and crash. So, why is this a different issue than stack overflows? Well, again, we cannot reach the return address. Moreover, there's another interesting complication. So, in the case of stack buffer overflows, we can just look at the assembly code and see how the stack is laid out. Now, the heap is much more dynamic. What the heap looks like depends a lot on the order of the calls that are done to malloc and free. So depending on the order and the sizes, the malloc library will find different patterns to allocate memory. Now this is a problem because it means it's much harder to understand what's actually happening. But it's also an opportunity for attackers. If the attacker can to some extent control when memory is allocated or deallocated, they also get some control over the memory layout. So this is also a benefit to some extent. Now, there are no return addresses on the heap, and if we don't know what block is next to us, we might not be able to overflow into a function pointer or something like that either. What do we do instead? We target the malloc implementation itself. So, we can target, for example, the metadata that is stored on the heap. So malloc has to keep track of metadata to know which block is how large, which blocks are used and which blocks are free, and so on. Well, it turns out if we understand how the malloc library works, we can abuse this metadata whenever we can overwrite it with a return with a buffer overflow. Here we have a very basic example of a heap overflow. In this case, we allocate two buffers on the heap. So the first one is username and the second one is password. Next, we use the getS function, which, as I mentioned before, is a super vulnerable function. There is pretty much no way to make getS safe. It will read as much data from the input as it can until it finds a new line. And it doesn't know or care about the size of the buffer. So, the attacker will provide two lines of input here, and both of the lines of input allow you to arbitrarily overflow these two buffers on the heap. Next, the program prints some information which will help us attack it, and then it frees the buffers again. This is what it looks like. So again, we randomize the address space. However, we no longer necessarily need to disable defenses because in this case, we don't target the stack. So for example, stack canaries that protect the return address are no longer relevant. Well, let's take a look what happens if we inject some data in there. First, two innocent values, Eric and then a new line and then Hunter2 as a password. We insert this into the Heap Overflow program, which reads it from the standard input and stores it into the buffers. Now the program works fine, because both of these values fit into the buffers. So what about the next one? So the next one, we inject too much data on the first line. These 32 A characters do not fit in the 24-byte buffer. So what happens? Well, it turns out it starts overwriting the metadata, which is right after the buffer. And as a consequence, the malloc implementation will see that something is wrong. And it complains that there's a double free or corruption. So it doesn't know if the metadata is corrupted, exactly what is wrong, but it knows that there is some issue and will warn us about it. Of course, as we've seen before, if we're careful enough to write the exact right values, it might not be able to notice. So let's discuss how the heap is organized. The stack, as we all know by now, grows downwards. The heap instead grows towards higher memory addresses. So at some point in the past, this was actually very useful because we would place the stack at the top of the address space and the heap at the bottom of the address space. And then we could just let them grow until they eventually ran into each other. So we didn't have to divide the address space between a heap and a stack at that point, which was considered useful back then. Of course, ideally we don't want the stack to grow too large, whereas in practice the heap can actually accommodate much larger objects. So the memory management is performed using in-band control structures, at least in the malloc library that we consider here, which means that we have the buffers and the metadata is right between the buffers. And when we have a heap overflow, we can manipulate this metadata, these control structures. And this can eventually be used with some work to execute arbitrary code. Now, again, as with the Stack Overflow, the exact exploit is dependent on the architecture and the operating system. However, in this case, the compiler doesn't really matter. The layout is decided mostly by libc. So libc implements malloc as a way to efficiently get memory without having to ask the operating system every single time. And the way that malloc works decides how you exploit a heap vulnerability. So we found that the exact attack depends on the implementation of malloc. For these slides, we will consider dlmalloc, which is Doug Lee's malloc library. Why do we pick this one? Well, it's of special historic interest and also practical interest because it's still used, because it's used in glibc, which is the GNU implementation of the C library and which is the default on many systems, including Linux. Now, modern versions of this library include a bunch of optimizations, and these make exploitation a bit more cumbersome. It's possible to still bypass them, but you need to be very careful in how you lay out the heap. So as an attacker, it makes it a bit more difficult. You need to allocate exactly the right data at the right time of the right size. And of course also free these things. So for these slides, we will consider the simple case where we don't need to bypass the optimizations. This is what the heap looks like. We have metadata and actual data. In this case, for the program, it first allocates a username buffer and then a password buffer. Well, these are contiguous with the metadata. So we first have a block of metadata, then the username, then again metadata, then the password, and then again metadata. As the heap grows upwards, it means that the addresses are increasing from the left to the right. So the later allocated object in this case has a higher address. However, do keep in mind, if you free some memory, it may be reused later on. So in this case, we cannot guarantee the order in memory. This shows again how important it is to keep track of how the heap is organized, how the memory allocation library works, and to use memory massaging where necessary. This is what happens when we perform the exploit. So we override the user buffer, the username buffer, and we put a lot of A's in it. Now, of course, the buffer is only 24 characters, so only 24 A's actually fit into it. Instead, the other A's are written on top of the metadata. So the malloc library will not like this. The heap is divided in chunks. So each chunk contains a part of the available heap memory, and a chunk can be of two types. A chunk can be either used or free. So used chunk, in addition to the metadata, simply contains the data that was stored by the program. So the malloc returns a pointer to a buffer inside the chunk, and this buffer is used to store the actual data that we care about. A free chunk is not currently used. However, it can be reused later. So when we allocate memory using malloc, it will first actually try to see if there's a free chunk it can already use. Only if all the free chunks are gone, or they are too small for this block of memory to be created. Only in that case do we need to go to the operating system to ask for more memory. Now, memory fragmentation is an issue here. If we have a lot of tiny chunks, we're not able to use them to allocate a larger buffer. So we don't really want that situation. How do we avoid it? We avoid it by always merging free blocks. So if we have any number of free blocks that are right next to each other, then these chunks will be merged into a single chunk that is still free and can now be used to allocate larger blocks. Of course, if we need a smaller block, that is also still possible, because we can simply split the chunk again, using only the part that we need for this particular allocation. Knowing this, how would we implement malloc? Well, it's actually fairly simple. First, it has to find a free chunk. Now, there is actually a free list that keeps track of all the free chunks to allow us to quickly go through the free chunks and see if there's any in there that is large enough to satisfy our request. So malloc is passed a size, and it simply compares the size against the size of the chunks in the free list. Now, modern implementations also have some optimizations here, for example by keeping multiple free lists for objects of different sizes. So this affects the order in which objects are reallocated. This is not something that prevents exploitation, but it's something that you need to be careful of to make sure that you massage the memory in the correct way. You might have to send the right buffer sizes to use the same free buffers that you wanted to, free lists that you want to use. Right, so for now we consider the case with no optimizations. We can bypass them if necessary. If not found, then we simply allocate more memory from the operating system. So this new memory becomes a free chunk, which is also added to the free list. If a chunk is, however, too large, we split it in two. So if we have a huge chunk and we want to allocate only a small buffer, we take the small buffer from the chunk and make it into a separate chunk. So the new part of the chunk that is not immediately used is then added to the free list. Now, we're allocating a block, so we're turning a free chunk into a used chunk. And we remove the chunk that used to be free and is now allocated from the free list to prevent later malloc calls from seeing it. Then in the metadata, we mark the chunk as currently in use. And finally, we return a pointer to the data area that is inside the chunk so that the caller can use it. Now free is implemented by first locating the chunk that contains the data pointer. So you have to somehow figure out, if we have this pointer, where does the chunk live? Well, this turns out to be very simple. The layout of the metadata is always the same. So we can simply subtract a fixed offset and find the location of the chunk metadata there. Next, we mark the chunk as free in that metadata, so to clarify that it can be reused later, and then we need to start merging. So because we want to prevent memory fragmentation, we need to merge the blocks at every time we free a block. And we only need to check two other blocks to see if we merge. If the next block is also free, we need to merge with the next block. If the previous chunk is also free, we need to merge with the previous one. Now this basically keeps an invariant where there are never two free blocks next to each other. And this means that we don't need to check multiple times. If there is a block that is already free next to us, we know that there's no other block next to it, because it would have been merged at the time that block was already freed. So we then add the chunk to the free list, which allows Malloc to find it if we're asking for more memory later on. This is what the heap metadata looks like. So this definition here was literally taken from the dlmalloc implementation. Struct malloc chunk includes 4 fields. However, it would seem that this creates an overhead of 32 bytes for every chunk. This is not the case. So actually, dlmalloc is very efficient with memory, and it will only use those fields that are necessary. And it turns out not all the fields are always necessary. In particular, the previous size is only needed if the previous block is free. If it's not free, this space will be used for data. The FD and BK pointers are used to maintain the free list. So if this block is not free, then it will not have a position in the free list. And we don't need the FD and BK pointers either. In this case, again, they're used for data. So the pointer returned by malloc always starts at FD, because malloc returns a used chunk, and the used chunk does not need a free list. So it reuses FD and BK to store the data. As we saw in the struct definition, each chunk has to store its own size. This is necessary to be able to, for example, find the next chunk, and also if we deallocate the chunk, to figure out how much memory we can actually release. So the chunk size is also the only field that is always in use. So both a free and a used block have the size field filled in. So this means there's only 8 bytes overhead per allocated block. So all the other fields are removed in case they're not needed. The size of a chunk is always a multiple of 16, which means that all the blocks are nicely aligned. So what do we do when we allocate? We simply increase the size of the allocation to this point. This is also relevant for exploitation because it means that if you can overflow a buffer by only a small amount, it might actually be part of the padding when the size was rounded up. So when we call malloc, the data size and overhead are computed together and then rounded up to a multiple of 16. This means that the 4 lowest order bits are always 0, because this is the case for multiples of 16. So instead, the implementation uses the lower order bits to indicate some of the status of the block. In particular, the prev in use field indicates that the previous chunk is in use. So if this bit is not set, it means that the previous chunk is free. And also, for very large allocations, malloc might decide to get them directly from the operating system, in which case it sets the other flag is ammapped. So what does this actually look like in memory? Well, it depends. It depends on whether the chunks are used or free, because a free chunk uses some of the data structures that are otherwise used for data to be stored as part of the chunk for the program. Let's see. If we have a use block that comes right after another use block, then as I mentioned, the overhead is only 8. So the size is stored here, and it has the prev in use bit set, which means that the previous block is also in use. Now, how do we know that this block is in use? Well, that information is stored in the next block. So in between there's the data. And strangely, the data actually straddles the boundary between the chunks. This is because the prev size field is also used for data, and the prev size field is at the start of the struct. So this field is only actually used for the previous size if the previous chunk is free. In this case, we have 2 use blocks following each other, so we do not use the prev size field. So we store data in it. Well, then the second one, let's say we have a used chunk, but it follows a free chunk. Now at the bottom, this is all the same. We have the data and it flows into the prev size field of the next chunk. At the start, we now have the prev size field stored. This keeps track of what the size of the previous chunk is. And it turns out we actually need this information to be able to do merging of free blocks. We also have the size of this block, which now no longer has the pref in use bit set. So, however, the next chunk does have the pref in use bit set to indicate that this chunk is used. Now, the next case, free after used. So let's say the previous chunk is used. It means that we don't need its pref size field. So the previous data is again at the start of the struct for the chunk. Then we have the size field as before, which also indicates that the previous chunk was in use. And now we get pointers to the next and the previous free chunk in the free list. So this data is now really used. It's no longer part of the user data because a free chunk doesn't contain any user data. Or at least the program cannot assume it will be reliably stored in a free block. So then after the end of the chunk, now we have the pref size field, which refers to the size of the current chunk. So the size of the current chunk is also stored in the pref size field of the next chunk. And then of course it stores its own size. And now the pref in use bit is no longer set, which indicates that the current chunk is free. Well, note that there's no free after free case here. This is because no such case can exist. If there are two free blocks next to each other, they will be immediately merged. So there can never be two free blocks following each other. Let's consider how the free list actually works. So you might think, wow, this guy is really going into a lot of detail about how malloc works. Why do I care? Well, you care because this is important for exploitation. Actually, the maintenance of the free list is a location where we're going to find the easiest place for an exploit of heap overflows. So bear with me. So the free list is used to find a free block to allocate. It's a doubly linked list using the FD and BK fields. So FD points to the next chunk in the free list and BK to the previous one. Now, when do we actually need to operate on the free list? We insert something into the free list at free time. And we also insert something into the free list when we're splitting a large block in malloc. So if the block is too large, then part of it will be used for the allocation and the other part will be split off as a new free chunk, which is why it needs to be added into the free list. Now, where we insert into the free list is in principle up to the implementation. So it's going to depend what memory reuse patterns look like. So it might be relevant for performance, and it's definitely relevant for attacks, because the way that memory is reused can shape the allocation patterns, and this affects memory massaging that you may need to do. So when are entries removed from the free list? Well, obviously in case of malloc, when you allocate a block, it's no longer free, but also merging free blocks in the free function. So when we merge blocks, then the old block no longer exists. So it's no longer in the free list. Now, how do we remove an entry from the free list? And this is actually where it gets interesting. So to remove an entry, what we need to do is to connect the previous and the next chunk directly to each other. Again, I copied the code straight from the implementation in the dlmalloc library. So the implementation simply has temporary storage, those are the capitalized BK and FD, stores the pointers there, and then uses those to connect the two blocks that are the previous one and the next one directly to each other in the free list, which means that the current block is left out and no longer in the free list. If we compile this code, this is what it looks like. So what happens is we take the BK and FD pointers and we actually use them to write to memory with these offsets. Okay, so we write two values, one with offset 24 and the other, then we use the pointers in the opposite way and we write with an offset of 16. Finally, we get to the fun part. So how can we exploit dlmalloc? And of course, similar approaches will also allow you to exploit other libraries, but then you need to figure out how their metadata works. First, assume we found a heap buffer overflow. So we can overflow a bunch of bytes right after a heap block. Contiguous is fine, this will do for us, but we need to be able to override some memory at least. Now, we override FD and BK, which means that we have to have a free block in there, right? Otherwise, with no free blocks, these don't exist and they're part of the data. And then we force the program to call unlink. So when we do unlink, of course, we remove the free block from the free list. And in this process, we perform the accesses shown on the previous slide. So a typical case is to merge blocks. When the block before this block is freed, then the object is taken off the free list, which means that the BK and FD pointers are used as shown on the previous slide. So unlink then writes chosen data, namely the FD pointer, at a chosen location, namely the BK pointer. And of course, also the other way around in this case. But it almost provides an arbitrary write. Of course, we use this in the end to exploit the program. This was all very abstract. Let's take a look what this looks like in memory. So let's see the layout that we have originally. We have two blocks, X and Y. Now X is used, and X is the location where we have a buffer overflow vulnerability inside. So we can write past the end of the data of X. And in that case, we overflow into Y. Now I'm saying here, chunk Y can be either. It doesn't need to be specifically used or specifically free. This contradicts what I just said, right? Well, actually it doesn't. Because what we're going to do is we're going to create fake blocks, in which case it no longer matters. So we overflow past the end of the data, and we're going to overwrite chunk Y to create new chunks. So this is what it looks like afterwards. So we're going to create two chunks, W and Z. Now chunk W will be a free chunk because we needed a free chunk. And chunk Z is only there to indicate that chunk W is actually free. Now chunk Z of course must be used because otherwise it could not be next to a free block. So the important part here is missing, namely the fact that there's no pref in use flag set on Z. This means that W is now a free chunk, which means that it has FD and BK pointers, which is what we wanted. So now picking the FD and BK pointers will, it turns out, allow us to select what we're going to write where. How can we achieve this? Well, we need to perform an operation on W that causes it to be removed from the free list. Now note that it's not actually even on the free list, but dlmalloc doesn't know that. dlmalloc sees that there is a free chunk and assumes it's on the free list. So that means it assumes it can safely unlink it as well. Right? Well, what would trigger taking W off the free list? It's really simple. It would be freeing X. And this is something that the program is actually likely to already do. So, how to get an arbitrary write? Get the victim to free X, which the victim might already do, or which the attacker might be able to trigger through the exploit that they send. Then dlmalloc, when freeing X, will consider whether to merge free blocks. It finds the next chunk W, and then looks for chunk Z, which follows it, and which says that W is free, because pref in use is not set. At this point, dlmalloc knows that it must merge X and W, because they are now adjacent free blocks, and adjacent free blocks are not allowed to exist. So, W is not on the free list, but dlmalloc still tries to take it off. It calls unlink, and then performs the writes that we discussed. At this point, we have an arbitrary write, which we can use to use the earlier exploitation techniques, and also some of the later exploitation techniques that we will discuss. So, this allows us to use the metadata to get an arbitrary write, even if we cannot directly overwrite anything else that is useful. As such, heap overflows are not only common, but also a very powerful exploitation technique. Now that we've seen the theory, let's see if we can actually exploit heap overflows in practice. So, how can we exploit an arbitrary write? Well, so far we've seen stack buffer overflows, where the return address is at a fixed offset from the buffer that we're overflowing. So this is very easy to reach. We could just look at the assembly code and determine exactly how far from the start of the buffer the return address was. And then we were able to compute the location compared to the buffer, which is nice. So for heap overflows, we get an absolute address that we can write to. Well, in this case, we need to know exactly where the return address is. And that may not be obvious. It may depend on the environment, it may be hard to predict, and so on. So it's nicer to find some attack target that we can use an absolute address for. We can use the so-called global offset table. So the idea is that, at least traditionally, library functions are loaded lazily. So whenever you, for the first time, you call a library function, only at that point will the operating system determine where the library function is in the library that you're calling, and at that point it will cache the pointer. So it looks up the pointer, stores it on the first call, and it's stored at a fixed location. So basically the first time you call this function, let's say printf, it will go to a stub. And this stub in the so-called PLT, the program linkage table, in the PLT, this stub will look up where printf is in the standard C library. It gets a pointer, it stores the pointer into the global offset table, or GOT, and afterwards the stub will call the printf function directly using the value stored in the GOT. Well, this means this pointer is in a fixed location, and whenever we change it, the next time we call this function, printf in this case, we will instead call whatever pointer we put there. So we can use this to get to our shellcode. Now, in this case, for this program, we have a printf call at the end, which we can use to hijack. So we hijack the printf GOT entry, and at that point, when we call printf, we go to our shellcode instead. Now we need to know where this GOT entry actually is. Well, fortunately, this is actually very easy. So let's compile the program and then use object dump to disassemble the program. Now we will find that there's actually a stub in there called printf at PLT, and this stub contains exactly the call that we're looking for. So we see here that there's an RIP relative offset, which is because this code can be moved in memory. So the PLT points to this particular pointer, right? Well, this is then the pointer that we want to hijack. So below we can actually see the stub that can be used to load the pointer into the GOT the first time that we call the function, which has an index 0, which is an index into the table of functions that need to be loaded from the library. An alternative is to use the readelf utility. So readelf is able to load an elf file and print some information about what is inside the file. And it includes the GOT entries. So here also we can find the address. Right? So it's easy to find the address. Whenever we overwrite whatever pointer is stored at this particular address, it will be called instead of printf. Now, a word of warning. So I've talked so far about dlmalloc, which is interesting because dlmalloc is actually the library used in the standard C library, for example on Linux, because it's used in the GNU implementation of the standard C library. So all these algorithms, as I described, are actually there, and it is possible to exploit dlmalloc in a similar way. However, dlmalloc currently, in its current versions, also contains extensive optimizations, which affect, for example, how free blocks are managed. Basically, the idea is to, as quickly as possible, find the right used block, also considering factors like TLBs, caches, and so on. So we want to make sure that we have temporal locality and so on. Now, for our purposes, what we really like is something that works exactly according to these algorithms in all cases, so that we don't have to manipulate the allocator first to get the special cases. So what I did is implement a new allocator, simplemalloc, which uses exactly the algorithms of the original dlmalloc. However, it removes the optimizations. Now, this means that it's much easier to give a simple example in my allocator simplemalloc, even though all the principles are still the same. And you would be able to escalate this to an exploit of the full malloc in the standard C library. That, however, I will leave as an exercise to the listener. I've shown the high-level approach to hijack control using dlmalloc. Now let's go into the gory details. So this is my proposal for the attack. So on the left we see the different fields that are there. Now, in the program that I've shown, there are two buffers, namely username and password, and both of them are in use. So we have two buffers, and in between there's only 8 bytes of size. So the user size goes before the user data, and the password size goes before the password data. Now also at the end, of course, there's another size field for whatever is the next chunk. So that chunk may be used or it may be free, it doesn't really matter. We only care about the fact that it actually shows that the password is in use. So this one points back to the password saying that it's in use. Well, this means that we cannot use password for the purpose we described before. We don't want it to be in use, we want it to be free. Because we want it to be merged with another block to be able to exploit the corruptions. So, as described, we actually create a new block that is free. Let's see how this works. So, originally the values are simply the block sizes, and keep in mind that they include the overhead, the flags, and the user inputs, which go into the data. So these user inputs at this point are harmless. They only become harmful when we overflow the block. So let's do that. So we're going to overflow the user data field into the size of the password block. Okay, so there we now write this. And this is the size of the new block W, as we also described in the high-level overview. So the new block W is actually 32 bytes. So it only takes up half the size of the original password block. This means that we can also fit inside yet another block, which is the Z block, which is also 32 bytes. However, this one does not have the pref in use bit set. This means that whenever malloc looks at W to be able to determine if it can be merged with another free block, it will check out this size field, see that it's not in use, and this means that W is actually free. So, when we free the user block, what it will do is it will look at W to see if it's free. Then it looks at Z to determine whether W is free, and finding that the pref in use bit is not set, it determines that W is free and then merges it with the username block, which is being freed. Right, so this is what we can achieve here. At that point, it will use the FD and the BK pointer to remove the block from the free list. Now note that we created this block just now. It's not actually in the free list, but it doesn't matter because dlmalloc doesn't check. There is actually no efficient way to check that because you'd need to go through all the entries of the free list. So we set the FD and BK pointers to perform the write that we want. In particular, the FD we use to set the location where we're going to write. However, we need to subtract 24 because as we saw, this was the offset of the field in the struct. So this is the offset of the BK field, just to be clear. So the FD pointer is going to be written based on the BK pointer. So we write here the got address minus 24. So this is the location where we're going to be writing something. Now in the BK pointer, we put the value that we want to write, which is going to be the address of the shellcode. Okay, so this is the way we need to set it up. Once we've set it up like this, in principle at free time, we should overwrite the got entry, and then the next call to printf will actually call our shellcode. Now one other thing to keep in mind here is which buffer to actually overflow. So we know that both buffers were actually vulnerable. However, we can also just write to whatever is inside the main body of the password block without any overflows. So we only really need to overwrite the size field of the username data. So after the size field, we just have the regular content data of the password block, which means that whatever we want to write there, we can write without any further overflows. Why is this interesting? Well, this means we actually need to overwrite only 8 bytes right after the end of the first block. So in principle, if the first block was an array of 64-bit integers, we only need an off by 1 error to do this, assuming at least we can manipulate the next block directly without an overflow. So that's nice, for the attacker at least. Well, Let's perform the actual full attack now. First of all, we're going to disable a bunch of protections. So, as I mentioned, the GOT entries these days are no longer completely lazily loaded, because obviously that's a major risk factor. So let's disable rel row, which makes sure that the relocations are read-only. Let's also disable for now position-independent code, because this also complicates the attack to some extent. So let's make it as easy as possible. Later we can always try and see if we can bypass these, for example by leaking information. But for now let's go for this. Again, we make the stack executable to make sure that our shellcode can actually run when injected into the environment, and then we perform the compilation. So we add simple malloc.c, which simply replaces all the calls to malloc and free. So it's bypassing the malloc implementation in the C library here. Well, as before, we disable ASLR, again to make the attack a bit easier. It's not a very big obstacle, it's just that we want to focus here on those elements that are specific to the heap overflow. Well, again, we compile the shellcode, we put the shellcode in a binary file, so we're basically stripping off the headers, and then let's go. We use Python again to inject the exploit. Now first, there's 24 characters of garbage, as we saw in the previous slide, and then we override the size field. Well, we already know that only the least significant byte of the size field actually needs to be changed. The remainder is all zeros and should also stay that way. So in practice, we only need to overflow, in fact, just a single byte. Not even the full 8 bytes, but in this particular case, just 1 byte. And then we put \n to indicate that the overflow of the first buffer is done here. At that point, getS will return, and the next call to getS will start reading stuff into password. And this is where the metadata for the new blocks is stored. First here, we have what we recognize as the GOT pointer minus 24 bytes. So in hexadecimal, that's actually 18. So we just subtract from the pointer 18 in hexadecimal, and then we put it there in little endian. Okay, we can actually insert the 0 bytes now, and this is because getS does not stop reading on a 0 byte. It only stops reading at a new line. So this allows us to actually write 0 bytes, which we were not able to do when working with regular strings. So next, we have another pointer, which is obviously the location of the shellcode again. And then we have two other values, which are the prev size field indicating the size of W, and then the size field of Z. Both are 32 or 20 in hexadecimal. We pipe this into the program, which we run while injecting the shellcode in the environment and removing the rest of the environment to ensure a reliable attack. Now, let's run this. What happens? Well, actually nothing useful happens. This is interesting. Why did this not work? Well, there are some reasons. And I would like you to take a moment and try and think what we're forgetting about here. There are actually two factors, and it may take a little bit of time to debug them. So, if you still want to think about it, pause now before I move to the next slide. The first problem is that we forgot about something. Actually, the free function performs two writes, as we can see on the right-hand side. It writes using fd, it writes to bk. And using bk, it writes fd. Okay, so these two writes are both happening. One of them actually did overwrite the GOT entry, as we were hoping for. The other, on the other hand, was corrupting the shellcode. So it writes 16 bytes into the shellcode, the value of the GOT pointer. Now, what happens? It was overwriting a string pointing to the shell. So it no longer had the correct name of the shell, and execve was failing. Now, execve failed silently because we have no error reporting in the shellcode. So as a consequence, the program did not start a shell, and we did not notice. So we need to somehow fix this. We will fix this by changing the shellcode to be more resilient to this particular corruption. We will see the new shellcode in a moment. However, this is not the only problem. Even if we fix the shellcode, the attack will not be useful in the way that I described it. The second issue is that the shell takes its commands from the standard input. So this may not be obvious when debugging the problem, but we're piping data into the program because it's using the input data to store in the buffer that is overflowed. Afterwards, Python will simply send an end of file, closing the file descriptor, and this will be a signal for the shell that there's no more input. And the shell, even if it is started, closes immediately and is not useful. So, one thing we could do to avoid this is to just forego interactive usage and instead provide command line parameters to the shell. So in that case, we have to modify our shell code to put the additional command line arguments in there. Now in this case, I will show a solution that still allows interactive usage of the shell without needing to change the shell code. So this is the new shell code, and we only insert the yellow marked line. So this line inserts 24 characters at that location, and these 24 characters use the value 0xcc. Now why this particular byte? So 0xcc is actually a breakpoint, also known as interrupt 3. So whenever, for whatever reason, we go into there, we will see it immediately, which helps debugging. Now why 24 bytes? So the exploit was going to write into the shellcode 16 bytes in. However, it's going to write 8 bytes. So just to be sure, let's make sure that all the 8 bytes nicely fit into the buffer, which is just garbage, and overwriting it does no harm. So 24 bytes, and afterwards there's the string, which is now not going to be harmed by our exploit. So this solves the first issue. Now, as for the second issue, and also just to have some diversity, I'll show a C program here that can address the issue. So why use a C program? Well, it's nicer, I guess, to use the attack from the shell, because obviously it requires less effort to write. However, it can be a bit of a hassle to debug, and it's definitely a hassle if you also want to provide interactive input, as the shell needs. So, how do we approach this? Some of the program in the main function we recognize from before. However, now we don't need to provide an argument. We only set the program name. We perform the computation of the shellcode address as before. So this is another benefit of using C code. It's easier to do computations like this. We print the value just to have some debugging information. And then we construct the exploit, which is done here. So we make a buffer and we write all the correct values into the buffer. Okay, well, again, we can do computations if we want, and we reuse, for example, the shellcode address that we just computed. Now we use the send input function before calling exec. Now this seems weird, right? So how can send some input to some program that wasn't even started yet? So what I'm doing here is I'm doing a fork. So at the point of the fork, it creates a child process, and the child process will execute the code inside the if, and then it exits. Whereas the parent process will continue its regular execution, which ends up executing the vulnerable program. So what happens in the program that we're starting as a child? Well, it's simply using a pipe to send the exploit, which is the first write. And afterwards, it keeps on reading from standard in and writing into the pipe. Now, anything that goes into the pipe will end up in the child process. So we're sending the input to the child process using this. And now we can have a fully interactive exploit that we can also easily debug. So this is the final functional attack that we can do. Again, we disable the protections. We will learn about these protections later on and about ways to bypass them. And then eventually we use the new shellcode and the new program to exploit our heap overflow. And now we have our first working proof of concept for a heap overflow.